The area of instrumental variables and what used to be called finite sample distortions in instrumental variable estimation is just an incredibly old one. It's one of the foundational fields of econometric theory, going back to the invention of instrumental variables in around 1925, 1926, all the way through the early work in the 1950s that was done by the Coles Commission and by people working with Dennis Sargent and the LSE, through trying to understand the behavior of instrumental variables estimators. So there's a giant tradition. Almost all of that work, certainly the early work and even in some of the more recent phases of weak identification, has focused on the most tractable case, which is the homoscedastic case. And under homoscedasticity, some really pleasant things happen. You know, the x prime x inverse sigma squared, that stuff works, everything factors out. But as you know, as practitioners, that's not really the most satisfying case. And the routine in econometrics these days and down to the undergraduate level is to do comma R all the time. And so basically what this is talking about, what we're talking about today, is what do we know about the non-homoscedastic case? So when I say non-homoscedastic case, we'll think about the reduced form errors potentially needing heteroscedasticity robust standard errors or hack standard errors, or if you're in a panel setting, it's going to be cluster, or it might be two-way cluster, something along those lines. We're actually not going to talk about specifics, is it cluster or hack or HR, because the moment you go there, you've crossed the line into this more complicated world, and it actually doesn't really make much difference which of these you're doing as long as you can get a consistent HR or hack standard error. But it turns out that that actually makes quite a bit of difference for for instrumental variables regression in the weakly identified case. So that's what we're going to be focused on. We're going to be focusing on weak IV in the heteroscedastic. We're going to call it the heteroscedastic case because it's tedious to call it heteroscedastic, hack, cluster, etc. But really we mean all of the above. Okay, so let me just, so I think this just says everything that I said. The outline, I'm going to do a little bit of the so what, but the fact is, Jim pointed out, if you're taking your Sunday afternoon to sit here, the so what is probably not super important, but I'm going to do a little bit of the so what, just for internal consistency. I'm going to talk mainly about detecting weak instruments. So let me also delimit a little bit what we're going to talk about. The primary focus of the talk is linear IV with a single included endogenous regressor. Now that is a special case. You know, Isaiah has been doing some really great work on nonlinear GMM and really complicated models and using Gaussian processes, and we could have done that. But it actually turns out that Sophie got a sample of 17 AER articles over the last 4 years that use GMM and IV and so forth, and 16 of the 17 have a single included endogenous regressor, and most of them have a single instrument. So that kind of seems like the important case in practice, and that's what we're going to talk about. Okay, so we're going to talk about the important case in practice. Linear IV with a single included endogenous regressor, and we'll talk about some extensions. We actually know a fair amount about that case, and so we're going to have some pretty concrete recommendations. So I'm going to go through detecting weak instruments. I'm going to say just a few words about estimation, and then Isaiah then will take our break, and then I'm going to hand it over to Isaiah, and he's going to talk about some weak instrument robust inference methods. You might have heard of Anderson-Rubin statistics, things like that, and but all in the HR, the heteroscedasticity case, and then we'll talk about some extensions and open problems. Okay, so what's a weak instrument? Weak instrument is one, loosely speaking, that has a small correlation with the included endogenous regressors. That would be if you have control variables in the problem, controlling for the control variables, it has a relatively small correlation. What does small mean? I mean, that's like a big question, so we'll try to be precise about that. When you have weak instruments, all heck can break loose. You can get bias in your two-stage least squares estimators. You can get substantial size distortions. Here's a very old picture from 1990 from a Nelson and Start's paper where they look at a distribution of the t-statistic in two-stage least squares. And the case of non-identification, where all the instruments are irrelevant, is the black line, the solid black line, and then it morphs over to something that kind of looks like a normal, but isn't really that normal, which is the dashed line. And then that's sort of going through the case of instruments being from irrelevant to intermediate cases to fairly strong. So needless to say, if the distribution of your t-statistic looks anything remotely close to the solid black line or the heavy dotted line, you know, your plus or minus 1.96 standard errors is just a bad idea. And so you're gonna have to figure something out. And this is just one example. And I'm not going to belabor this because I think people understand that's it. That's the problem, and that's why you're here, and you want to try to avoid that. A relevant question is, yeah, okay, so this is fine. So the econometricians are going to say this is really important in theory, but then there's a question of is it important in practice? And it might not be that important in practice. I mean, if everybody always had strong instruments in all of their applications, then this wouldn't be an issue. And so this would just be a bunch of econometricians writing papers for econometricians. So as I mentioned, Sophie went and collected data from the 17 AER articles, and I'm not going to describe the DGP that they put together. Isaiah's going to go through that, but Isaiah and Sophie put together a DGP, and on the x-axis here is, now we're doing a simulation. So the population value of the first stage F statistic is on the x-axis. And then what's on the y-axis is the median of the t statistic. So in some of these cases, there's like one instrument, and if there's one instrument, you can't really talk about bias because moments don't exist, but you can talk about where the median of the t statistic is, and that kind of normalizes it by the standard error. So, and what you can see is that when you're down somewhere below this range, there's a vertical line at 10, and somewhere down below to the west of 10 is a mess where you can get t-statistics in this DGP that are under the null hypothesis, not centered around 0. They can be centered around 1, right? A t-statistic centered around 1, that's like off by a lot, right? Okay. But then if you've got pretty big first stage Fs, 40, 50 in population, then things seem to, at least from, this isn't talking about size or anything, but at least it's starting in the center of it's in the right place. And then the relevant question is, yeah, well, how much of this really do you actually find in empirical work? And so here's some other statistics from this sample. And so this is actually the reported first stage F. So this is the first stage F that people report in their is that right? This is the histogram of reported first stage Fs? Yes. So this is the histogram of reported first stage Fs. And what you can, it's really interesting. So there were 108 specifications among these 17 papers. The 17 papers, one of them had 2 endogenous variables. So for this purpose, we're throwing that away. And then one of them didn't report enough evidence for us to figure out what the first stage Fs were. So we have 15 papers that are here. And I'll be corrected if that's wrong. Okay.
There were a few more that reported other things, p-values. These are the ones that reported first stage Fs.
Okay. Anyway, there's 72 of these specifications for the first stage Fs or less than 50. And those are what's plotted here. And what you can see is that there's a fair number of them that are, 5 or 10, sort of in that zone where things were really messing up. There's this big spike between 10 and 15, which is like, that's pretty interesting. We could speculate about why that might happen to be, and we'll come back to that. That's actually, I mean, it's sort of from my perspective, it's like, whoa, this is kind of amazing, but on the other hand, it's kind of not exactly what you'd like to see. So, and we'll talk about that. And especially in the simulations, we'll talk about that. And then there's a few cases where they have really strong F statistics. But of course, we know, like, not every problem is a weak identification problem. So then there's an interesting question of what do people report? So really the main thing that I'm talking about is the first stage F isn't a well-defined object because there's a number of different things that you could actually do. And I'm sure those of you who've run Stata, IV Reg 2, there's like this comma first or whatever, there's this mass of stuff that's printed out. And that includes the Kleiberg and Papp statistic, it includes heteroscedasticity robust first stage F if you've done a comma R, comma VCE cluster or something like that. If you don't do that, then it's going to print out the non-heteroscedasticity robust first stage F. One thing that's not printed out, but you could print out, is something called a Montiel-Alea-Pfluger effective first stage F. So the main point of this talk, of my piece of it, is to sort through all of those different possibilities and to give a super precise, clear directive about which one you should be using. Okay. So here's what people report. Okay, here's what people say they do. So the purple ones are Kleiberg and Papp statistics, and then the brown ones they don't say. They just say these are first stage Fs. And that's like, this is really interesting. Our conjecture is that people don't realize that the Kleiberg and Papp statistic is the heteroscedasticity robust first stage F. And that's why all of these ones less than 5 are the Kleiberg and Papp statistic, because they're called the Kleiberg and Papp statistic, not the heteroscedasticity robust first stage F in the paper. And that whatever referees or whatever are not fully aware of that subtlety. Stata doesn't help with its printout. So I'm not sort of saying that this is like anybody's fault, but I think it represents some confusion. And then there's these other ones that are bigger. We went back, or Sophie went back and did some reverse engineering to try to find out, this is what people say they do, and then Sophie went back to do some reverse engineering to see what people actually really did. And here we've clumped the Kleiberg and Papp with the robust ones, and so that's why they're shaded the same color, and those are these ones that are lower. The ones that are the really high F statistics, those actually turned out to be mainly the non-robust F statistics. So if you compute the first stage F that's not heteroscedasticity robust, that tends to be the bigger ones. And so if that could be correct, the correct thing to do, because maybe in those designs there's no heteroscedasticity and there's no hack. But on the other hand, if you're thinking, well, gosh, the reason I'd want to do robustification is because the standard errors might be too small. If there's heteroscedasticity or cluster or something, then that would be a reason why you might actually find these large non-robust first stage Fs. All right, so that's the review of the literature, and there's going to be a lot more on this simulation in Isaiah's part. Okay, here's our recommendation. So I just want you to notice. Okay, so there's 4 possibilities, except 2 of them are the same. So doing Kleiberg and Papp and doing heteroscedasticity robust first stage F are actually the same thing. So that's option 1. Option 2 is doing non-robust, and option 3 is doing this thing called the effective first stage F from Montiel-Alea-Pfluger 2013 JBS. None of these do the third one. Okay, none of these do the effective F statistic. That is our recommendation. So our recommendation is that you do the effective F statistic. So basically the next 30 minutes of the talk is explaining to you why I think that's right. And the reason I'm going to spend 30 minutes on it is that there's really clear theory saying that that's the right thing to do and nobody does it. Okay, everybody does. Actually, there's really clear theory that both of these are the wrong thing to do in the heteroscedasticity case. So I'm just going to walk through that. So there's going to be a very simple lesson, and we're going to march through the algebra, and then you'd have learned a thing from this first half of this talk, and that'll be hopefully worth, well, it's raining out, so. Okay, so our recommendation is you use this thing, you report the first stage effective F statistic, and you can compare it, and we'll talk about what you should compare it to. There's some critical values you could compare it to, or you could use this rule of thumb, and I'm going to come back, of 10, and I'm going to come back and we're going to talk about that, and Isaiah's going to talk about that too. If you're doing this as a pre-step or a pre-diagnosis, then, if it's greater than 10, then you might want to use strong instrument methods. 2-stage Z-squares, for example. And if it's less than the cutoff, 10, or the critical value, if it's less than that, then you're going to have to use some weak instrument robust methods for inference. And Isaiah will talk about that. Okay, so and then there's a list of things you should not do. So do not report the p-value of a test of pi equals 0, because it's not really, the issue is the first stage coefficient equal to 0 in population. That's 0 is too small a number. It actually has to be far enough away from 0 that you're not going to be dividing by 0. And so testing 0 is not a useful thing to do. Don't report the non-robust first stage F. So don't report the usual robust first stage F, except it turns out that when k equals 1, when there's a single instrument, that it turns out that the first stage F and the effective F are exactly the same thing. So I'll walk through that. Don't report the Kleiberg and Papp statistic, which is actually the heteroscedasticity robust first stage F. Don't compare the heteroscedasticity robust or Kleiberg and Papp statistic to Stock-Yogo critical values, and that's because the Stock-Yogo critical values are under homoscedasticity. This is just something else altogether under heteroscedasticity, and you'd think it would line up, but it doesn't line up because the stuff is tricky. Okay, and don't, just because if you're a referee and they've got like a first stage F of 6. Don't reject the paper. Tell them to go and use heteroscedasticity robust methods. Because if you just tell them to reject the paper, you're contributing to this publication selection bias problem. Whereas we have good methods for doing inference when when you're in weak instruments. Okay, and I wasn't refereeing on any of these papers, but that spike at 10 is not terrific. Okay, so what I'm going to do is I'm going to march through the algebra. Remember, the main point of this is to explain in a very specific and concrete way why this Montiello-Lea-Pfluger statistic is the right one to use, the effective F statistic is the right one to use, and why in general the non-robust and robust ones are not the right ones to use. So when I say right and wrong, if you're in a world where it's truly homoscedastic, then these are all the same and it doesn't matter. But we're interested in the world that everybody lives in empirical work where you think that probably isn't right, or maybe you've had to use hack standard errors. There's a reason that you want to use HR or standard errors, and so we're going to want to have the methods align with those reasons. Okay, so this is the setup. First stage equation says that there's some instrument Z relating to the single included endogenous regressor X. There might be some control variables W. The coefficient of interest is beta, which is the coefficient on X and Y. It's going to be interpreted as a causal effect. And then so that's the object of interest. There's the reduced form. The reduced form is obtained by substituting the first stage into the structural equation and then solving out, and then you get a coefficient on the z's. If you look at the coefficient of y and the pair of equations for y and x, that is a pair of reduced form equations, both of which are expressed in terms of the z's. And then by doing that substitution, what you find is that the coefficient on the reduced form for the y equation has on z for the y equation is written as pi times beta, and that pi times beta is this famous form, which is then sort of how, the way that you deduce beta is you can get a whole bunch of different, you use 2-stage Z-squares. If you have a single included endogenous instrument, you can take the ratio of delta hat to beta hat, and that's delta hat to pi hat, and that's going to give you an estimate of beta hat, and that's just the IV estimator. Okay, so that's the setup. OLS is in general inconsistent. I've included the control variables W, and I am now going to throw them away for the rest of the talk because you can always just project them out and do Frischwa. So they're there, but they're gone, all right? Or they're gone, but they're there, whichever you want. Okay, So that's the setup, throwing away the control variables, two conditions for instrument validity or instrument relevance and instrument exogeneity. We're going to be assuming throughout that instruments are exogenous. That's part 2 of the paper, right? And here, this is just the technical thing having to do with making sure that the instruments are relevant. So that's what we're going to focus on. Relevance, the relevance condition is that they have to have some covariance with the included endogenous regressor, or equivalently in this notation here that pi is non-zero. To be a strong instrument, they've got to be sort of better than that. And then once you have these two conditions, you can just derive the IV estimator. So I'm including the standard derivation, or I should say the first derivation of the IV estimator here, which is just by writing out this covariance and then noting that the covariance of z and epsilon is, this covariance between z and epsilon is equal to 0. And then because the covariance between z and x is non-zero, you can divide through, and that's going to give you the moment condition. And then you just plug in sample moments. Those sample moments are also just the ratio of delta hat to pi hat. Okay, so everybody's with me? So clarifying questions are absolutely fine if I'm not being clear. Okay. Okay, so two-stage squares, you have multiple instruments, then you can just take the predicted value from the first stage. So one way to write two-stage squares is you just do that regression of y on the predicted values from the first stage regression, which is y on x hat. There's the famous x prime z, z prime x, z prime z, whatever it is, formula, you know, and so you got that guy there, and that's another way to write it. And then you can also write it, if you notice that x prime z, z prime z inverse is actually, that's the coefficient, that's the estimator for the first stage equation for pi hat. You can also rewrite this in terms of these OLS estimators for pi hat and delta hat, which are the reduced form, the two estimators in the reduced forms, the first stage and then the reduced form equation for y. So there's various estimators for two-stage least squares. The problem, so if you just stare at this, any of these expressions, but I like to stare at the last expression for two-stage least squares, basically the problem of weak instruments is that you're dividing through by something in the denominator, and if that thing is close to 0, then you got a problem. And so that it's basically, and in fact, if the true values of pi were 0, then that thing in the denominator is kind of like a chi-squared, and you can get some chi-squared with, and you can get some values that are really small, and there's a lot of noise in the denominator, and that can totally mess up your distribution. So the problem with the weak instruments problem is really just a glorified divide by 0 problem, and you just need to be careful that you're not doing that. And that's one way to say that is that you need to make sure that in population that denominator is not too close to 0. Otherwise, that can really mess up the sampling distribution of all of your IV statistics, or all of your two-stage least squares type statistics. One thing we're not going to do is talk about a much broader class of problems, of which this is the leading case, but is only one case, which is this whole family of stuff that goes under the terminology of weak identification, which gets into nonlinear GMM and not even GMM circumstances, but cases where you've got some parametric restrictions where you could be close to a boundary. There's some nice papers on that. There's the Nelson Starts paper, 2006, Journal of Econometrics, and then an Andrews Chang Econometrica paper that go through this much more general area, much more general treatment. We're not doing that. Okay, so we're talking about detection, and it's in the linear case where we've got a single X, a single included endogenous regressor, and we got 3 choices. Okay, there's 3 choices. Choice number 1 is we could use the plain old-fashioned non-robust F statistic. So remember, the world, we're imagining that we're really in the HR world, but you've just done this anyway. Okay, so maybe it's a good thing, maybe it's not, but you've just done it anyway. The other possibility is you just do a heteroscedasticity robust. Well, so let's just stare at these for a second. These are all our familiar friends. So we're just looking at Remember, in the non-robust formula, it's just z prime z inverse sigma squared v, and so that's just the inverse of that. Here it's just the inverse of the heteroscedasticity robust covariance matrix estimator, which is sigma pi pi. So I've denoted if we take pi hat as the estimator, then its variance is going to be sigma sub pi pi, and then the estimator of that variance is sigma sub pi pi hat, and then you sandwich that in between in the inner product, and that's your F statistic, okay? Testing that pi is equal to 0. And then there's this weirdo thing, which is some hybrid, which is this Montiel-O'Leah-Pfluger, and you look at it and you can say, well, I know why nobody uses this, which is that somehow it's got the numerator of the non-robust thing, but then it doesn't actually, but then there's something funny going on in the denominator where it's not using the pi's here, but it's using the pi's in some sort of trace down here. So there's like something really peculiar going on. It actually, you can rewrite it as the non-robust times a scale factor, and that scale factor is the ratio of the variance to some trace of the that involves the covariance matrix of the heteroscedasticity robust covariance matrix and the moment matrix of the z's. Where did that come from? And so we're going to have to try to explain that. This is the big intuition, okay? So this is the big intuition. So if you stare at two-stage least squares, look at what's in the denominator of two-stage least squares. So in the denominator of two-stage least squares is this pi hat, q hat, zz, pi hat. That's what it is. That's x prime z prime z inverse z prime x. That's what it is. It actually is a case that the non-robust statistic is measuring that. It's just that it's getting the standard errors wrong. The heteroscedasticity robust isn't measuring the right thing. It's measuring something else. So it's doing a classic econometrics deal, which is it's measuring the wrong thing, but getting the standard errors right. And so what this effective F statistic does is it says, okay, we want to measure the right thing. We want to measure the thing that's in the denominator. We're not going to be able to get the standard errors right, but it turns out this trace guy gets them right on average. Okay, so that's it gets them right on average because by this normalization, it turns out that the eigenvalue is it's like you're taking an inner product of chi-squared or non-central chi-squared, where the eigenvalues are now, by this normalization, bounded between 0 and 1. So it's transformed the problem where we don't know exactly what the distribution is, but we can bound the distribution and we can estimate, we can do a lot of approximations to it. Okay, so that's the, and I'm going to give you some examples. So now what we're going to do is going to go through some examples. And so I'm going to do an example in the k=1 case that is a single included endogenous regressor where everything is just really easy. And then it turns out, in that example, I'm going to give you a case. It's actually not that surprising. It's more sort of to get the algebra juices going. It's not that surprising because what you can show is that, yeah, you could actually have a pretty weak instrument, but if your non-robust estimator has really got the standard errors wrong, you could get a really big first stage F, and it's not going to pick up your weak instrument because you're just getting the standard errors wrong. So that kind of makes sense. What's a little bit more subtle is then I'm going to go to an example. Maybe I have that. No, I'll go to it. I'll give you my more subtle example in a minute. It's a great example. Okay. All right. Here, so we're going to make some distributional assumptions. These are high-level distributional assumptions where we're going to assume that these reduced form estimates, the pi's and the deltas, which are just going to be the regressions in respectively of x on z and then y on z, that these things are jointly asymptotically normally distributed, and then you've got some consistent estimator. So I guess I should say on the consistent estimator thing, so like if you're thinking, oh gosh, I'm really interested in the hack problem, but I want to use Kiefer-Vogelsang fixed B asymptotics, we're not there, okay? So we're just doing Newey West with consistency. Or if you're saying, gosh, I know that in cluster, if I've got a large sample T and I only have a few groups that I'm clustering by, that really I should use that Hotelling t-squared distribution, or I should use a t-distribution with a number of groups as the, and we're not doing that either. Okay, so we're not doing that. We're just like, you've got consistent estimators. Okay. So as I say, there's a lot going on here. So there's and then okay. So then the next assumption that we're going to make is that actually we're going to take this central limit theorem thing, and we're just going to pretend that it holds. So we're just going to say it actually holds so that delta hat is normally distributed and pi hat is normally distributed. So there's actually, in some sense, it's like a really easy assumption. Sure, okay, we'll make that assumption. There's a ton that's going on underneath the hood there. So one of the things I mentioned, which is that we're ruling out, for example, fixed B asymptotics, we're ruling out the non-standard cluster asymptotics, that sort of thing. Second thing that's going on under the hood is that this harkens back to this old 1950s, 1960s literature where you're assuming that the instruments are fixed and that the errors are normally distributed, and that you know, in the case of what's called the limal K statistic and work on that, you actually know what the reduced form variance matrices are. So there's an aspect of this literature that is what we're doing here that's really old stuff, 50s, 60s years old. More recently, there's this is all sort of justified. One way to justify all of this is through weak instrument asymptotics. And there one needs to consider drifting sequences to get all of this to line up in terms of the asymptotic justification, where you actually think that pi is pretty small compared to the sample size. And that's like the case when these first stage Fs would be in the, the not so big area. Hirano and Porter, 2015, and also in a 2012 paper provide limit experiment interpretations of all of this stuff. Then there's a question of uniformity going from the unidentified all the way to the the well-identified case, and Andrews and Cheng go through that. So there's a lot of things going underneath the hood, and we're not going to talk about any of that stuff. They're just going to actually plug in this normal assumption. But there's a lot of good theory justifying that, and it provides good approximations too. Okay, this is the example. So I don't know why I called it a homework problem, because it's a great homework problem. Okay, so if you teach this stuff to graduate students, this is a great homework problem. They will really understand weak instruments, or at least this aspect of weak instruments when they come out of it. All right, so we've got two instruments, one included endogenous regressor. The instruments were orthogonal to each other. So we set them up so they're just normalized it so the instruments were orthogonal to each other, orthonormal, so they have variance 1. Okay? Simplify things. And then sigma, remember sigma is the covariance matrix of the pi hats and the delta hats. Now, if it were homoscedastic, it would have this Kronecker structure so that sigma squared epsilon and sigma squared v is going to come out here, and it's all going to be multiplied by the z prime z matrix, and then everything cancels in a beautiful way. And remember, that's like the first 70 years of this literature, and that's not what we're going to do. But we're going to make it almost as simple, so it has a Kronecker structure, but it's not quite the same covariance matrix. Remember, the QZZ matrix is diagonal, and we're going to allow one of the instruments, so think of omega as being big. So we're going to allow one of the instruments to have what we usually think of as the heteroscedasticity problem, which is the standard errors, the OLS standard errors are too small. Okay, so the usual standard errors are too small, so the real standard errors should be bigger. They should be bigger by a factor of omega squared. And the other one, just to make the example interesting, we're going to go the opposite direction, and the OLS standard errors are too big, and really if you knew the nature of the heteroscedasticity or the hack, the robust standard errors would be a lot smaller. Okay, so that's the setup. So we're making one little tweak, which is one of the instruments, the hack works against you, and one of the ways it works for you. And it turns out that that screws up both of these two statistics. So it's pretty easy to see why it's going to screw up the non-robust statistic, because the non-robust statistic is going to get the standard errors wrong on one of the pieces, and so it's going to think that the standard error is really small for one of the pi's. So it's going to say, hey, I've got one really good instrument, and so I've got my F statistic is really big. And so the non-robust is just going to be misled because it's computed the standard errors wrong. It turns out that the robust one is misled. It's computing the standard errors right, but it's computing the wrong thing. So it says, gosh, one of my instruments is terrific because it has the heteroscedasticity is working in my favor and it's making my real standard errors really small. And if you were doing efficient GMM would say, great, that's the instrument I'll use, but you're not doing efficient GMM. You're doing two-stage least squares, and two-stage least squares is weighting both of these two instruments, and one of them is not necessarily a strong instrument. In fact, one of them is getting the standard errors wrong, so it turns out this key parameter is the fact that the HR is looking at the wrong thing is driving the robust one to infinity, when in fact you could actually have really bad, instruments that are actually quite weak. So the heteroscedasticity robust one is going to say one of my instruments is super, the heteroscedasticity robust F statistic is going to go off to infinity, but in fact you're actually in a weak instruments problem. So both of these you compute. So it's actually not so great, in the sense that if you're sitting down at Stata or R or whatever, you compute the non-robust F, it's 73. You compute the robust F, it's 87. You say, I'm good, but you're not, okay? And then you compute the Montiel-O'Leary first stage effective F, and it's 4. And that's the one you need to use, okay? We will discuss this. All right, so I'm going to work out the case for k equals 1 first. Okay, k equals 1, single included endogenous regressor. And remember, I'm just assuming that delta hat and pi hat are normally distributed. So remember the reason I'm going through all of this? You can say, why do I have to suffer through this? The reason I'm going through all of this in such detail is that nobody does this. And everybody should do this. Okay. Or at least nobody who gets published in the AER. Okay. Okay, so it's convenient to write, I'm going to use this equals with a little squiggle over it to say I'm going to give a representation of delta hat as this mean of delta, and then a normally distributed thing, psi sub delta, and that psi is just going to have this covariance matrix that's in general the HR covariance matrix, the heteroscedasticity robust covariance matrix, and so I'm going to let me give you that's the first thing I'm going to do is I'm going to use this representation. Let me give you one other piece here. If I look at if I were to, it's very convenient to have something like an OLS regression of Z on the epsilons, epsilon being the errors in the structural regression. So that's something that comes up in the algebra. And I'm going to give that a name, psi sub epsilon, and it actually can be expressed as a linear combination of the delta hats and the pi hats. It's actually delta hat minus pi hat beta. And that's like a key linear combination because remember, in population, delta equals pi beta. Okay, so delta hat minus pi beta is supposed to have like a mean of 0 and then some noise. And actually the noise it has is equivalent to regressing epsilon on the z's. Right, so that's all just equivalent algebra, and then that means I can represent it in terms of a normally distributed thing, which is going to be the psi from the delta minus the psi from the pi. So that's just going to be a normal random variable. It's convenient to standardize these things because I'm going to talk about some things being big and some things being little, and for that it's nice to have all the random variables to have variance 1. So we're going to standardize the random variables by dividing them through by a standard error. So I'm going to write pi plus psi as something called lambda plus z. And so z sub pi is going to be a standard normal random variable, in this case k equals 1. And z sub epsilon is going to be another standard normal random variable, and they're going to be correlated with each other. So I've just taken these and divided them through by the standard error. This is a key thing. This parameter lambda is a key object that is going to be describing the strength of the instruments, and has a very natural interpretation. The interpretation, what it is it's pi divided through by its population heteroscedasticity robust standard error. So it's the population value of pi, and you divide through by its HR standard error. And if that's big, then that's going to be something that's going to be an indication of a strong instrument. If it's small, that's something that's going to be an indication of a weak instrument. Okay. And then I'm going to do one more trick here, or one more convenient device, which is I'm going to orthogonalize z epsilon and z pi. In general, they're correlated with each other because, of course, there's endogeneity here. So I'm going to do some orthogonalization, and then that orthogonalization is just in terms. So since they're both jointly normal, I can project z epsilon on z pi, and then I'm going to have a normally distributed residual, and that's going to be useful for representations of the variables. Okay. So with that, I can just do, I can move from the IV representation being the delta hat over the pi hat, and then I'm just going to do a couple of steps. I'm going to add and subtract, pi hat beta, and then going to sort of notice that pi hat beta divided by pi hat is equal to beta. And then this thing here, I'd already argued, is equal to psi sub epsilon. And then so I've got this expression, and now I'm just going to standardize by dividing through by standard deviations. So now I'm going to do this projection, and the reason I'm going to do this projection, right now this is a pretty informative thing because it says that the IV estimator is the true thing plus a ratio of variables, a ratio of normal variables. One of them has mean 0 in the numerator, and the other one has mean lambda in the denominator times a scaling factor. It's useful to break this up in general because these two variables are correlated. That means if you take the expectation of if the moments were to exist or if where it's going to be centered, these things, because they're correlated, that means that this thing is in general going to have some bias or non-central distribution. The reason I'm being careful about using the word bias is that moments don't exist here, but the distribution will be shifted a little bit. Okay. So if you then break this up by projecting z epsilon on z pi, and then taking the residual, you're left with this term, which I'll call a bias term and I'll call a noise term, and both of those are misleading because the bias doesn't have a mean, and so it's not really biased, but it's kind of a centering, is where the thing is centered. And the noise is noisy, but so is the bias term because the bias has this random noise in it too. But it's sort of a centering piece and a non-centering piece. I'm going to focus on the centering piece. All right, so this is like a bias type thing. One thing you can see immediately is that the amount of bias, if you will, is going to be determined by lambda. And if lambda is equal to 0, then these two z's cancel each other, and then you're just left with this guy right here. In the homoscedastic case, that's the p-lim of OLS. So what this says is that right away in the unidentified homoscedastic case, beta hat IV is centered around the p-lim of OLS with what? With a ratio of two normals, so with Cauchy noise. Okay, so it's Cauchy, so you take OLS and then you add a Cauchy to it, which is like not the greatest thing ever. So that's you can sort of see what the weak instrument problem is. But the bigger lambda is, if lambda is really big, then lambda is going to swamp this randomness here, and then you're just left with a normal in the numerator and lambda in the denominator, and actually that gives you your usual large sample distribution, your usual like two-stage g-squares textbook distribution. So lambda is the key object, and so we're going to have some inference about what that is. Okay. So instrument strength depends on lambda. Strong instruments is lambda squared, goes to infinity. Irrelevant is lambda is equal to 0. I just described that case. In the old literature, this lambda squared is called the concentration parameter in the literature that worked on Gaussian Edgeworth expansions. Okay, so here's a fun little calculation. So it's like everything, all these E's need to be in quotation marks. These expectations need to be in quotation marks. But you've probably, if you've heard of some of this old literature, maybe you've heard of Nagar expansions, and then you've sort of phased out and not done. So we're going to do a Nagar expansion. A Nagar expansion is you pretend that moments exist and you just like linearize and you see what happens. And it turns out in this case it's incredibly simple. So I'm just going to take the ratio. Remember in the homoscedastic case, this is the p-lim of OLS. So it's the inconsistency of OLS. So we're looking at how far off the bias is of IV relative to the p-lim of OLS. And I'm just going to, so now I'm putting an expectation where one doesn't really belong, but I'm just putting it there. And so now I'm just rewriting this by dividing through by lambda, and now I'm doing an expansion, which you can kind of pretend is justified if lambda is sort of big. And then I have a leading term in that expansion. And then actually the only randomness appears in the numerator, but it's a standard normal. So the standard normal just has squared, has a mean of 1. And so this term is minus 1 over lambda squared. So if you said that I want to have, suppose that I want to have the Nagar bias be no more than 10%, that says you need lambda squared to be 10. Okay, so lambda squared is the non-centrality parameter of the first stage F statistic. So that's sort of like an idea of where 10 might, where does 10 come from? That's like a way that you could think about the number 10. Okay. There are better ways, but that's a way to think about it. Okay. So, so now if we've done that, then we can go back and we can look at, well, what are these different, what's the robust F and the non-robust F, how do they play out in this case? And just a little bit of algebra. So with the thing about traces of matrices, is that when the traces of matrices are actually, when the matrices are not matrices, but they're scalars, the traces are just like the thing, and then they all cancel, and the numerator and the denominator cancel, and that's what happens when k equals 1. So it turns out that this trace guy for the effective F just is just the robust F. So it just gives you the robust F. And in that case, then the robust F just is just going to be lambda plus z sub pi. There's a typo there. Lambda plus z sub pi quantity squared. It's a non-central chi-squared with non-centrality parameter lambda squared. So remember, we wanted to do inference about lambda. The robust F in the k equals 1 case is exactly what you'd want to do to do inference about lambda. It's also equal to the effective F. The problem with the non-robust is that it's almost what you want, but it's then times something weird. And what it's times is, well, actually it has a great interpretation. It's times the ratio of the variance of the heteroscedasticity robust variance to the homoscedasticity only variance. And so if you got it wrong, if the homoscedasticity gets it wrong, then the first stage F has the wrong standard errors if it's non-robust. And so it's just going to give you the wrong number. And so it's pretty easy just to come up with an example where the first stage F gets it wrong if it's non-robust, but it gets it right if it's robust. In terms of thinking about estimation and testing here, let me just say one other comment. If you wanted to have an estimator of lambda, you could just take that first stage robust F and subtract 1, and that would be an estimator of lambda. But another thing you could do is you could say, maybe what I want is I want to make sure I want to formulate a hypothesis that says that that like the Nagar bias, if you will, is no bigger than 10%. And so I want to test whether or not lambda is sufficiently large to ensure that that's the case. Well, what that actually says is I want to test the null hypothesis of lambda squared is equal to 10 against the alternative that lambda squared is bigger than 10 and less than 10. And so to do that, you would actually use the distribution of the robust first stage F statistic, which is this non-central chi-squared, and that gives you a critical value of 23, which is actually that's the Monteaglio-Fluger critical value for the k equals 1 case, which is 23, which comes from this non-central chi-squared. Okay. This slide just basically walks through example where you can get this completely wrong in the non-robust case simply because you get your non-robust standard errors wrong. So if the non-robust standard errors are too small, then the non-robust standard errors are too small, then you're going to get the you could potentially be confused and make an incorrect understanding that you've got a really big first stage F, but that's just because the standard errors are wrong. Okay. Okay, so here's the interesting one. So this is for k equals 2, and so let me walk through these different things, and then I'll let me walk through these different things. So there's k equals 2, and so what we have here is we have one instrument where the heteroscedasticity robust standard errors are really big, and you don't realize that when you do two-stage least squares, or when you use the non-robust standard errors. And the other instrument, the heteroscedasticity robust standard errors are really small, and you don't realize that when you do non-robust standard errors. And it's going to mess up, one of them is going to mess up the non-robust statistic, one of them is going to mess up the robust statistic, and the effective F is going to get it right on average. Okay, so that's what we're going to go through. All right, so the homework problem has two steps. It has, first of all, if you just take the definitions of these different things, plug them in, and go through all of the algebra that we've done, what do things look like? And then the second one is, once you've got these things here, we're going to assume the weak instrument nesting, and then we'll just take some limits. And it turns out that if I let omega squared go to infinity, so one of these has like really horrible HR standard errors, and one of them has really, really great HR standard errors, then you can actually show the following results: that the non-robust goes to infinity, the robust goes to infinity, the effective F goes to a chi-squared 1. So the probability that it is less than 10 or less than that 23 critical value is basically 1. So you're going to conclude correctly, and then actually it turns out that also in this case, where OLS, two-stage least squares is centered, is actually at the p-lim of OLS. So you actually have completely weak instruments in this example from a two-stage least squares perspective. Okay, I don't know whether everybody wants to march through this. It's sort of like I could just leave this. Yeah. Oh, I don't know. It's like it's all right. I'll do one of them. Okay. So here, this is the non-robust. So remember, I said that pi hat is going to be pi plus that random noise, and then I rescaled it to make sure that the stuff was standardized, and that gave me a lambda plus z sub pi. And by doing that, I had to pull out this covariance, the heteroscedasticity robust covariance matrix for the pi's, and then I'm still left with q hat in the middle. This is the key thing. That remember, in two-stage least squares, q hat's there in the middle, and then I've got the same thing on the other side, and I'm dividing through by that, and then I can just take these various limits. This is because q hat, the instruments are orthonormal in this particular example. Then you can just plug everything in, and then you just get this expression. And so now, sort of, I think if I stare at this expression, basically what this first stage F is doing is that it's weighting by it's one of these is going to be measured. One of these OLS is measuring it far too precisely, and one of it OLS is measuring it far too imprecisely. But the fact that it's measuring one of them far too precisely gets OLS confused and blows up that F statistic. So OLS thinks I've got a great first stage instrument, when in fact that's just because it hasn't been doing it heteroscedasticity robust. And you can just work through that same logic with the other cases. So I think I probably won't work through that logic. There's the homework problem solution is sketched out here. I would urge you to assign this to your graduate students. It's a great exercise. Okay. First stage F, so maybe that's the one piece of mystery here that is worth looking at. Why does this effective F work? Well, the effective F works because remember the non-robust F statistic, it's measuring the right thing, but getting the standard errors wrong. The thing is, you can get the standard errors right at least on average, because the standard errors on average are going to be measured by the trace of that heteroscedasticity robust variance matrix, and you can estimate that consistently anyway, even if you're not using it as the thing you're sandwiching in the middle. You can use it to correct the standard errors. And so that's exactly what this effective F statistic does. And in this example, it's the first stage F plus divided by, it's the non-robust first stage F, but then you divide by this trace of this robust covariance matrix, and that's dividing by exactly the right thing to get it right on average. Now, it's not exactly like a chi-squared 2 distribution. It turns out everything loads onto one of these in this example, so it's a chi-squared 1 distribution. But whether it's chi-squared 2 or chi-squared 1 doesn't matter. You're going to be recognizing that the instruments are weak for the purpose of two-stage least squares. Okay. And then there's some fancy things that Montiello, Leo, and Pfluger have to try to get a better approximation to that distribution, so they actually realize that would be a chi-squared 1. All right, so that's the whole idea. So we're going to use this, and so one way to write it, you can make it look really simple. It's just it's just this lambda times z pi with an H matrix, and then the H matrix is just this thing. And the thing that's nice about this, let me just say one thing that makes this, I think that this expression looks nice, because if you think about the H matrix, first of all, it's symmetric. Second of all, it's dividing through by its trace. Well, if you think about a symmetric matrix divided through by its trace, the trace is equal to the sum of the eigenvalues, but the sum of the eigenvalues, if it's a symmetric matrix, all those eigenvalues are positive. So that says that you've made it so that this matrix H has eigenvalues that are at most 1 and at least 0, and sort of they have to average, the sum of them has to equal k. So you sort of that's not exactly right. The sum of them has to equal the sum of the sum of these has to equal 1, excuse me. The sum of these eigenvalues has to equal 1. And so what you've done is you've got this thing in this, you've got an object where it's like these chi-squareds hitting this matrix that has these eigenvalues that are all between 0 and 1, and they sum to 1, and that's a well-behaved object. And there's the family of things you can do, like you can go to this. These guys found some old, like 1940s, 1950s approximation to this distribution as a non-central chi-squared with some adjusted degrees of freedom, and so you can program that up, and they have, and so that you can program that up if you want to get critical values for this. Okay, so there's a variety of different things you can do, and so one of them is a testing approach. And so even though the exact distribution of this guy is a little bit, you can simulate it, that kind of defeats the entire purpose. Having to simulate a first stage F defeats the entire purpose of doing the first stage F, which is you want something simple to tell you whether you then have to do something hard. So I think doing the simulated version of this is overkill. There's this approximation to critical values that they provide using these Paetnik-Nagar critical values, and so and then they have a limit. They have some upper bound on those that they tabulate up as simple critical values, and that's something that you can use in the paper. There's an additional approach you can use, which is you could just use a rule of thumb. That's the bottom, so you could just say, what about 10? And Isaiah will see whether that works or not. And then there's this is the econometrician's approach, which is that really what we want you to do is we want you with probability 1 to do the right thing if they're weak, but with probability 1 to be able, if they're strong, to be able to do two-stage least squares. So the answer to that is you should compare it to a sequence that's indexed to the sample size, and so that's comparing it to kappa sub n. So you could just compare it to kappa sub n. And then the econometrician stops, and you have to figure out what kappa sub n is. And one option is setting kappa sub n equal to 10. Okay. Okay, so let me make some additional comments about the k equals 1 case. So the k equals 1 case, it turns out that this actually, it's very simple, and we have not this approximate Patnick thing, but we actually know exactly what the distribution of the effective f and the robust f is, which is exactly a non-central chi-squared. So there's a couple of different things you can do. You can either say I want to have this critical value of 23, which is the 95 percentile of the non-central chi-squared with a non-centrality parameter 10 and 1 degree of freedom, which would correspond to this Nagar bias of 1/10. Or alternatively, you could do something like a testing thing. You say, in the worst case, I want my two-stage t-squares t-statistics to have a size distortion of no more than 10%. So if I'm doing a 5% test, I don't want it really to be no more than a 15% test. Yeah, I know it's completely arbitrary, but you could say that, and if you did, that would give you some different critical values. Those are the so-called Stock-Yogo critical values for size distortions, and those give you, like, for a 10% size distortion, that would give you 16.4 instead of 23. So there's some really concrete things you could do here. We are actually not going to recommend any of those. What we're going to recommend in the k equals 1 case, in the very special case when you've got one included endogenous regressor and one instrument, which was like 14 of the 17 papers or something.
It's like roughly almost half the specifications.
Half the specifications. Okay, so lots and lots. So this is like, I think we all know from practice that this is an important leading case. In that particular leading case, we're going to suggest that you use a heteroscedasticity robust Anderson-Rubin statistic all the time and not bother with this first stage F stuff. Okay, so I won't say any more than that. But I think that there's a reason, I think there's valid reasons to think about doing this first stage F stuff once you have more than one instrument. Okay. What if you have more than one included endogenous regressor? So the problem with more than one included endogenous regressor is that people just haven't worked out this stuff in the HR case. This is like a great thing. This is like a great thing. The student who does the best on this problem set, you can set them on this problem. Okay, so there's some good procedures out there. There's some minimum eigenvalue of a Krag-Donald statistic. There's a related thing that Sanderson and Windmeyer have proposed, that saying, suppose you have one, the question is, do you think you have one good instrument and one bad instrument? Do you think all of the instruments are bad? So if you have more than one, do you think one of them is identified? If you have more than one included endogenous regressor, then the question is, well, is one of them identified? Is the other one not identified? Are they both not identified? And so how do you parse that out? And so so the complete non-identification is one possibility. There's like a partial identification thing, or one strong, one weak. And so this Sanderson-Windmeyer statistic gets at, well, suppose one is okay and you want to check on the other one. The trouble with all of this stuff on this slide is that everything on this slide is either homoscedasticity only, which is the non-robust, or it's getting the standard errors right but measuring the wrong thing, which is the robust version of it. So this is not really worked out for the HR case. And so I think more work is needed on this. Okay, let me say one other comment. Suppose you were going to do suppose you're going to do GMM instead of two-stage e-squares. So I made this digression. In my homework problem example, it actually is the case that if you were going to do if you're going to do efficient GMM, you actually have one terrific instrument because it happens to have this heteroscedasticity that makes its variance super small if you only knew to put all the weight on it, and that's what efficient GMM would do. The problem is, in the world of weak instruments, the GMM estimator he's got an even more complicated distribution. It depends on how you do the first stage. It depends on, if you're going to do CUE, and I think, and then doing, you know, sort of testing whether or not you can then do GMM in the second stage is also something that needs to be more work on in the HR general case. Okay, let me show you something about screening on first stage F. So I mentioned this at the beginning, that it made me kind of nervous to see that spike at F equals 10. And that kind of it's just got to be the case that there were some of those papers that didn't get into the AER because they had less than 10. And if you screen on less than 10, remember, it's not the sample that matters, it's the population. And you could be in a weak instrument case, but then you happen to have that, you know, 10.3 number that then gets you into the paper. And the trouble is, if it's really less than 10 and you happen to, then you select on only those realizations, you can have a mess. And this is just an example, and I think you'll probably talk about that. But you can really have a substantial selection problem because you are, you know, pulling from the tail what appears to be strong, but really it's not. So you're getting a messed up distribution. So that was a very non-technical statement, but I think you can kind of get that. Let me say just a few words on estimation. So we haven't talked about estimation very much. I haven't talked about estimation, and Isaiah's not going to talk about estimation. We wanted to bring what has happened in the literature, say in the last, let's say, 10 years in the estimation world, and almost all of it is bad news, except there's one really interesting piece of good news, maybe. And we have differences of opinions about how important it is, but we'll find out, okay? But almost all of it is bad news. So one of the pieces of bad news is there used to be this folk theorem that, you know, everybody who stared at this problem, like all the greats, Sargon and Anderson and Tile and Rothenberg and everybody, they stared at this. You can't have an unbiased estimator. It can't exist. And it turns out that's correct. And that was proven a few years ago by Hirano and Porter. So that's life, okay? So there's other things that we've known for a long time, which is lack of moments existing. I will say there's this one, the final bullet is that if you a priori know what the sign of the first stage is, so if you a priori know pi, remember this is pi conditional on the instruments. But if you know pi conditional on instruments has a known first stage sign, then it turns out that you can do this really cool thing that Isaiah and Tim Armstrong invented or applied in this case or figured out. Like some Russian had figured it out in the case when you're just doing the inverse of the mean, and then these guys said, oh, if you can do it in that case, you can do it in IV. You can get an unbiased estimator if you know that the first stage sign is positive. And then actually that works pretty well. If it happens to be a strong instrument, it turns into just like two-stage Z-squares or IV estimator in the strong instrument case. So it's pretty cool. It hasn't had a lot of practical applications, so we'll see. It's a cool idea. But you got to know you can't kind of know the first stage sign. You can't think that it's probably something. It's got to like be it, okay? K equals 1, things are more problematic. And there was a paper that at least I found really influential by Mikhail Kolasar in 2013, which is his job market paper. And what he showed is that if you have different lates for the different instruments, then we know the two-stage squares gives you a certain late, and we know all about that. Limmel doesn't need to be in the convex hull of these lates. So you can have like this instrument and this instrument and this instrument are estimating these things, and that Limmel's over here, okay? So that's like really problematic. So you don't even have control over the estimand in a way that you would have control over the estimand with two-stage squares. So a lot of this family of procedures like Limmel, which was thought until this paper as being potentially a really good idea because it seems to have better bias properties than two-stage least squares in sort of semi-weak or weak cases, you now suddenly realize, well, bias for what? You know, it's like bias or unbiased. That's all of that is in the case that the estimands for all the instruments, the lates are all the same, but as soon as you were in this world where you want to have some control over your late, and then I think you're just driven right back to two-stage least squares, and there's not, I think, any real silver bullets here. The other comment is that things get more complicated when you start doing nonlinear GMM, and there's not a lot of constructive stuff that's been learned. So aside from Isaiah and Tim's paper, I think most of what's been learned in the last 10 years has actually been kind of negative results, where we thought we knew some stuff that was pretty positive in the homoscedasticity only case, and sort of now we think maybe that's not so great.